The James Webb Space Telescope recently photographed something that should not exist in the same image. A galaxy more than 10 billion light years away, magnified 30 times by the bending of space itself, looking faint, red, and completely dead. No new stars, no bright core, no visible engine of any kind. It looked like a fossil drifting in the dark. But when scientists tracked the motion of the stars inside it, they discovered those stars were moving far too fast. Something invisible was pulling them. Something with a mass of 6 billion suns was hiding at the center, giving off nothing, emitting no light at any wavelength, sitting in total silence. Webb did not photograph a monster. It photographed the quiet that a monster leaves behind. If this is the kind of science that pulls you in, a like and a subscribe genuinely help this channel keep going. We put real work into every one of these, and your support makes the next one possible. Are you comfortable? Now let's begin. There is an image sitting in the archives of the James Webb Space Telescope that does not look like much at first glance. It is not one of the vivid, sweeping portraits of nebulae painted in infrared gold and crimson. It is not one of the deep field images crowded with thousands of galaxies spiraling across billions of years of time. At a casual look, it could almost be mistaken for sensor noise or a smudge on a lens. A faint red arc, a stretched, distorted smear of ancient light, sitting behind a cluster of brighter white objects that look far more interesting by comparison. Most people would scroll past it. Most people would not give it a second thought. That would be a mistake. Because hidden inside that faint red arc is one of the most scientifically important and deeply unsettling discoveries Webb has ever made. And the reason it is unsettling is not because of what the image shows. It is because of what the image hides. The object in the image is a galaxy. Its catalog designation is MRG M0138. That name does not mean anything poetic. It is an identifier assigned by astronomers for a galaxy that was first noted as part of a gravitationally lensed sample behind a massive galaxy cluster. But the story behind that designation is anything but ordinary. MRG M0138 is more than 10 billion light years from Earth. That number deserves a moment to settle. 10 billion light years. Light is the fastest thing in the known universe. It crosses roughly 186,000 miles every single second. It can circle the entire Earth more than 7 times in a single second. And the light from this galaxy has been traveling for more than 10 billion years to reach the mirror of the Webb telescope. That means we are not seeing the galaxy as it is right now. We are seeing it as it was when the universe was roughly 3 billion years old. The universe today is approximately 13.8 billion years old. So the light in this image left its source when the cosmos was barely into its first quarter of existence. When you look at MRG M0138, you're not looking across space alone. You're looking back in time. You are watching an era when the universe was still assembling its first major structures, when galaxies were young, chaotic, and in many cases still aggressively forming stars at rates that dwarf anything we see in the modern cosmos. That context matters enormously for what comes next, because this galaxy, this ancient system from the early universe, is not doing any of that. It is not forming stars. It is not glowing with the light of new stellar generations being born out of collapsing gas clouds. It is not active. It is not busy. It is not producing anything at all. By every measurable standard, MRGM0138 is dead. It is a quiescent galaxy, a system that has shut down its star formation and now drifts through the cosmos as a collection of aging stars with nothing new being added and no mechanism that scientists can identify that would restart the process. A dead galaxy, 10 billion light years away, seen as it was when the universe was only 3 billion years old. That alone is strange. Galaxies at that age were supposed to be in their most productive phase. The early universe was dense with gas, rich with raw material, and gravitationally primed for collapse. Star formation should have been happening everywhere, and at enormous rates. Finding a galaxy that had already finished, that had already burned through its cycle and gone quiet while the universe around it was still roaring with activity, is like finding a campfire that has already turned to cold ash while every other fire in the forest is still blazing. To appreciate just how strange this silence is, consider what other galaxies look like at the same cosmic epoch. When Webb surveys the deep sky at comparable distances, it finds galaxies drenched in activity. Their spectra are streaked with bright emission lines, the unmistakable signatures of hydrogen gas being heated by newly born stars and collapsing into fresh, stellar generations. Their colors skew blue, because young, massive stars burn hot and radiate intensely at shorter wavelengths. Their morphologies are often ragged and asymmetric, because they are still assembling themselves through mergers and gravitational interactions, pulling in streams of gas from the cosmic web, swallowing smaller satellite galaxies, and converting all of that raw material into stars at rates that can exceed 100 solar masses per year. Some of them are so prolific that astronomers classify them as starburst galaxies, systems in a temporary frenzy of production that will eventually exhaust their reserves and slow down. But at 3 billion years into cosmic history, even the calmer galaxies are still actively forming stars. The gas supply is abundant. The gravitational conditions favor collapse. The default state of a galaxy at that epoch is busy. MRGM 0138 is not busy. Its spectrum shows none of the emission lines that mark active star formation. Its color is red, dominated by the cool light of aging stellar populations that formed long ago and have been slowly fading ever since. Its morphology, to the extent that it can be reconstructed through the distortion of the gravitational lens, is smooth and settled, not the chaotic tangle of a galaxy still under construction. Every observational indicator points in the same direction. This galaxy shut down while the universe around it was still in full production. It is not merely old, it is prematurely old. It aged out of its productive phase far earlier than the cosmic environment would suggest. And it did so completely, with no residual star formation, no lingering pockets of activity, no sign that the process could restart. That premature death is itself a scientific puzzle. But it is not the discovery. That is just the context. The discovery is what scientists found hiding at the center of that quiet, dead, ancient galaxy. Something they could not see. Something that emits no light at any wavelength. Something that gave itself away only through the movement of the stars around it. Before we get there, we need to understand how Webb managed to see this galaxy at all. Because at 10 billion light years, even a full-size galaxy is unimaginably faint. The photons arriving from MRGM 0138 have been traveling for more than 10 billion years. They've been stretched by the expansion of the universe, their wavelengths pulled from visible light deep into the infrared, which is exactly the range that Webb was built to observe. But even Webb, with its 6.5-meter gold-plated mirror and its position at the second Lagrange point 1 million miles from Earth, would struggle to resolve the internal details of a galaxy at that distance. This is where the universe itself stepped in and offered something extraordinary. Between us and MRG M0138, there is a massive cluster of galaxies, a dense congregation of hundreds of galaxies bound together by gravity, sitting directly along our line of sight. That cluster is not just a visual obstruction, it is a lens, a gravitational lens, and it is one of the most powerful natural instruments in the observable universe. The idea behind gravitational lensing goes back more than a century. In 1915, Albert Einstein published his general theory of relativity. Among its many predictions was one that seemed almost absurd at the time. Massive objects do not just pull on other objects through gravity, they bend the fabric of space and time around them. A star warps the geometry of the space it occupies. A galaxy warps it more, and a cluster of galaxies containing trillions of solar masses of ordinary matter and dark matter combined warps space on a scale so vast that light passing near it follows curved paths rather than straight lines. This is not a metaphor. It is not a poetic way of describing attraction. Space itself, the actual geometry through which light travels, is physically deformed by mass. A photon traveling through flat, empty space follows a straight line. A photon traveling through the curved space near a massive object follows the curvature. If the alignment is right, if a distant source of light sits behind a massive foreground object, from our point of view, the foreground mass bends the light paths around it, focusing and magnifying the distant source in the same way a glass lens focuses and magnifies a distant object. Einstein predicted this. Arthur Eddington confirmed a version of it during the solar eclipse of 1919, when starlight was observed bending around our own star. But the full-scale version, the kind that uses an entire galaxy cluster as a lens, was not observed until decades later. Today, gravitational lensing is one of the most powerful tools in all of observational astronomy. And in the case of MRG M0138, it was not just useful, it was essential. Without it, the discovery at the heart of this story would have been physically impossible. Here is what happened. The massive galaxy cluster sitting between Webb and MRG M0138 bent the light from the distant galaxy around itself. The curvature of space around the cluster acted like a magnifying glass, spreading and amplifying the image of the background galaxy. The result was dramatic. The distant galaxy, which would otherwise appear as little more than a faint dot even to Webb, was magnified by approximately 30 times. 30 times larger, 30 times brighter, 30 times more detail resolved in the infrared light that Webb collected. The lensing was so strong that it did not just produce one image of the galaxy, it produced four separate images of the same galaxy, each one following a different light path through the curved space around the foreground cluster, arriving at the telescope from slightly different angles and with slightly different magnifications. This is a phenomenon known as strong lensing, and it is the gravitational equivalent of seeing the same object reflected in multiple mirrors, arranged around a central mass. Each image is real. Each one carries genuine light from the distant galaxy, and each one shows the galaxy from a subtly different perspective. Among those four images, one was magnified far more than the others. That image, the most stretched and most detailed, became the focus of the study. It was observed using Webb's near-infrared spectrograph, one of the most precise instruments ever placed in space, capable of splitting infrared light into its component wavelengths and reading the chemical and kinematic fingerprints of objects billions of light years away. The team that studied it was led by Andrew Newman of Carnegie Science in Pasadena, California, with Richard Ellis of University College London serving as senior author. Their findings were published in the journal Science in June 2026. What they found in that magnified image began as a confirmation of something astronomers had already suspected. MRGM0138 was old. Not just distant, but genuinely ancient in terms of its stellar population. The stars inside the galaxy were not young, hot, blue giants. They were old, cooling, reddish stars, the kind that form when a galaxy has long since stopped producing new, stellar generations. The galaxy's spectral signature told the same story from every angle. No emission lines from hot hydrogen gas collapsing into new stars. No signs of active star-forming regions. No ultraviolet excess from young, massive stars burning through their fuel. Everything about MRGM0138 said the same thing. This galaxy had shut down. Its fire had gone out. Now, picture this as clearly as you can. You are looking at a galaxy from when the universe was 3 billion years old. The cosmos around it, at that same era, was exploding with activity. Other galaxies at similar distances were forming stars at tens or even hundreds of times the rate of our own Milky Way today. Gas was plentiful. Gravity was pulling it together in every direction. The raw ingredients for star formation were everywhere. And yet, this galaxy had already stopped. It was already finished. That raises an obvious question. What stopped it? What could have shut down star formation in a galaxy that existed during the most productive era in cosmic history? To answer that, you would need to look at the very center of the galaxy. And to look at the center, you would need something beyond even Webb's extraordinary resolution. You would need the magnification that only gravitational lensing could provide. And that is exactly what the team had. Thanks to the 30 times magnification, Webb could resolve details inside MRGM0138 that would normally be invisible at such distances. The near-infrared spectrograph did not just photograph the galaxy, it mapped the motions of its stars. Every star in a galaxy is moving. Stars orbit the center of their galaxy the way planets orbit a star. Pulled inward by gravity, held in orbit by their own velocity. The speed at which a star moves and the shape of its orbit depend on the total mass enclosed within its orbital path. A star orbiting close to the center of a galaxy is responding to the gravitational pull of everything inside its orbit. If you can measure how fast the stars are moving at different distances from the center, you can calculate how much mass is contained at each radius. This is the technique known as stellar dynamics. It is one of the most reliable methods in all of astrophysics for determining the mass of objects that cannot be seen directly. It is the same method that earned a Nobel Prize in 2020 for measuring the mass of the supermassive black hole at the center of our own Milky Way, Sagittarius AI star. That black hole, roughly 4 million solar masses, was weighed by watching how its gravity moved the stars around it. The principle at the center of MRGM0138 is identical. The distance and the difficulty are not. But Sagittarius A star is only 26,000 light-years away. The stars around it can be tracked individually with infrared telescopes on Earth. MRGM0138 M0138 is 10 billion light years away. Individual stars cannot be resolved at that distance, even with Webb, even with lensing. What can be measured is the collective motion of the stars, the average velocity and the spread of velocities at different positions within the galaxy. If stars near the center are moving significantly faster than stars further out, more than what the visible mass of the galaxy can explain, then something else is there. Something massive, compact, and invisible is warping the gravitational field at the core. That is exactly what the data showed. The stars near the center of MR GM0138 were moving too fast. Not slightly too fast. Not ambiguously too fast. The velocity dispersion in the central region was dramatically higher than what the mass of the visible stars alone could account for. The gravitational field at the center of that galaxy was being dominated by something that was not contributing any light, not at any wavelength, not in any part of the electromagnetic spectrum that Webb or any other telescope could detect. There was a mass at the center of that dead galaxy, a compact, invisible concentration of gravity that was pulling the surrounding stars into faster orbits and betraying its presence through motion alone. And the scale of that mass, once the calculations were complete, was staggering. This was not a modest concentration. This was not a typical galactic bulge or a dense cluster of old stars mimicking a central mass. The number that came out of the stellar dynamics analysis was approximately 6 billion times the mass of our Sun. 6 billion solar masses, compressed into a region that Webb could not resolve even with 30 times magnification, meaning it was extraordinarily compact. There is only one known type of object in the universe that can concentrate 6 billion solar masses into a volume that's small and remain completely invisible across the entire electromagnetic spectrum. A supermassive black hole, a dormant one, a black hole that is not actively feeding, that is not pulling in streams of gas, that is not heating matter to millions of degrees and blasting radiation across the cosmos. A black hole that is sitting in silence, surrounded by the aging stars of a galaxy that has already exhausted its fuel, exerting its gravitational influence on everything nearby, and yet producing no light of its own. No glow, no jet, no accretion disk, no signal at any wavelength. It is there only because the stars say so. Their motion, their speed, the pattern of their orbits, all of it points to the same conclusion. Something enormous is anchoring the center of that galaxy, and it is invisible. This is the heart of the discovery. This is what the title means when it says the most terrifying thing Webb has ever photographed. Webb did not photograph the black hole. No telescope can photograph a dormant black hole. There is nothing to photograph. A black hole that is not feeding emits nothing. It absorbs light. It warps space. It moves stars. But it does not announce itself. It doesn't cooperate with our instruments. It simply sits there, invisible, patient and massive, beyond comprehension. What Webb photographed is the galaxy around it, the faint red arc of ancient starlight, bent and magnified by a cosmic lens, carrying within it the kinematic signature of something that should not be possible to detect at 10 billion light years, but was detected anyway because the universe itself provided the magnification. The previous record for measuring a dormant black hole using stellar dynamics was roughly 700 million light years. That was already considered a remarkable achievement, pushing the limits of what ground-based and space-based telescopes could accomplish. MRGM0138 sits more than 10 billion light years away. That is roughly 15 times farther than the previous record. It is not an incremental step. It is a qualitative leap in what astronomers can now observe. Enabled by the combination of Webb's infrared sensitivity and the natural magnification of gravitational lensing, and the number at the center of it all, 6 billion solar masses. To put that in perspective, the supermassive black hole at the center of our own galaxy, Sagittarius EY star, has a mass of roughly 4 million suns. The black hole hiding in MRGM 0138 is approximately 1,500 times more massive. Imagine taking every star, every planet, every asteroid, every grain of dust in 1,500 copies of our Milky Way's central black hole, and compressing all of it into a single point of infinite density. That is what is sitting in the center of this quiet, ancient galaxy, giving off nothing, visible to no instrument, detectable only because the stars around it cannot lie about what is pulling them. And here is the detail that should stay with you. This black hole is not dangerous to us. It is more than 10 billion light years away. It poses no threat. It will never reach us. Its gravity affects only its immediate surroundings. The terror is not physical. The terror is conceptual. Because if a black hole this massive can sit inside a galaxy that looks this dead, this faint, this unremarkable, and remain completely invisible until the precise alignment of a gravitational lens and the most powerful infrared telescope ever built conspire to reveal it, then how many more are out there? How many ancient, dormant galaxies scattered across the early universe are hiding similar masses at their centers? How many quiet images in the Webb archive contain the gravitational fingerprints of monsters that no one has looked for yet? That question leads directly to the next one. If the black hole is invisible and the galaxy is dead, how did the scientists manage to separate the black hole's gravitational signature from the mass of the galaxy itself? How do you draw a line between the gravity of 6 billion solar masses of black hole and the gravity of the billions of ordinary stars surrounding it? The answer involves one of the most precise measurements ever performed at cosmological distances. And it begins with a spectrograph, a strip of infrared light and the tiny differences in how fast stars move depending on how close they are to something they cannot see. To understand why the discovery inside MRGM 0138 is so remarkable, you first need to understand what makes this black hole different from nearly every other supermassive black hole scientists have studied in the distant universe. And the difference comes down to a single word: silence. Most of the supermassive black holes astronomers have identified in the early universe were found because they were loud. Not loud in the way a sound is loud, but loud in the way that light is loud. They were active. They were feeding. They were surrounded by vast quantities of gas, spiraling inward at tremendous speeds, forming a structure called an accretion disk. And that disk, heated to millions of degrees by friction and compression and gravitational energy being converted into radiation, was glowing so brightly that it outshone the combined light of every star in the host galaxy. Sometimes by factors of hundreds, sometimes by factors of thousands. These are the objects astronomers call quasars. The name is short for quasi-stellar radio source, a term coined in the 1960s when the first of these objects were discovered and initially mistaken for stars because of how bright and compact they appeared. A quasar is not a star. It is the visible signature of a supermassive black hole that is actively devouring matter. The gas does not fall in quietly. It spirals. It compresses. It collides with itself, and in the process it converts gravitational potential energy into electromagnetic radiation so efficiently that a single quasar can outshine an entire galaxy containing hundreds of billions of suns. This is what a quasar is. For decades, quasars were the primary way astronomers studied supermassive black holes at great distances. They were beacons. You did not need to resolve the black hole or even the galaxy around it. You just needed to detect that extraordinary light. The brightness itself told you that a supermassive black hole was there. And the characteristics of the light, its spectrum, its variability, its luminosity, told you roughly how massive the black hole was and how fast it was consuming material. This method has been spectacularly successful. Thousands of quasars have been catalogued across cosmic history, some of them shining from when the universe was less than 1 billion years old. The most luminous among them are visible from more than 13 billion light years away. They have given astronomers an extraordinary window into the population of supermassive black holes that were actively feeding in the early cosmos. But there is an enormous problem with this approach. It only finds the ones that are eating. Think about it this way. Imagine you are trying to count the number of predators in a vast dark forest. You cannot enter the forest. You cannot see through the trees. The only tool you have is a microphone that picks up the sound of feeding. Every time a predator catches prey and tears into it, you hear the noise and mark the location. Over years, you build a map of predator activity. You know where they hunt. You know when they are most active. You can estimate how many are currently feeding at any given time. But what about the predators that are not currently eating? The ones that are resting? The ones that are waiting? The ones that finished their last meal long ago and now sit motionless in the dark, invisible to your microphone, undetectable by any instrument that relies on the sound of consumption. You know they exist. Every predator has to stop eating eventually, but your map does not include them. Your census is biased. You're counting only the noisy ones and missing every quiet one entirely. That is almost exactly the situation astronomers face with supermassive black holes in the distant universe. For decades, we have been building our understanding of how black holes grew and evolved in the early cosmos by studying the loud ones, the quasars, the active galactic nuclei, the objects that announce themselves with light, the quiet ones, the dormant black holes that had already finished feeding and settled into silence, were invisible. Not because they were small, not because they were unimportant, but because they gave us nothing to detect. A dormant, supermassive black hole emits no light. That statement is easy to say, and difficult to truly absorb. Inside the event horizon, nothing escapes. That is the defining characteristic of a black hole. But even outside the event horizon, a dormant black hole produces no significant electromagnetic radiation because there is no infalling material to heat up. No gas spiraling inward means no accretion disk. No accretion disk means no friction, no compression, no conversion of gravitational energy into photons. The black hole simply sits there. It curves space around itself. It holds its gravitational grip on the stars and gas and dark matter in its vicinity. And it emits nothing. Not in visible light. Not in infrared. Not in ultraviolet. Not in X-rays. Not in radio waves. Not at any frequency in the entire electromagnetic spectrum. It is, for all practical purposes, a hole in the observable universe, a region where mass exists, but light does not. This is why measuring the mass of a dormant black hole at cosmological distance is a fundamentally different problem from measuring the mass of an active one. For active black holes, astronomers have several techniques at their disposal, none of which require resolving the black hole's gravitational influence on individual stars. The most common is called reverberation mapping. It works by observing how fast the gas in the accretion disk responds to changes in the quasar's brightness. When the central engine flares, the flash of radiation travels outward and excites gas clouds at various distances. By measuring the time delay between the central flare and the response of the surrounding gas, astronomers can determine the size of the region. Combining that size with the velocity of the gas, derived from spectral line widths, gives the mass of the black hole. The technique is elegant and has been used to weigh hundreds of active black holes across a wide range of distances. But reverberation mapping requires an active black hole. It requires an accretion disk that varies in brightness. It requires surrounding gas clouds that respond to that variation. A dormant black hole has none of these things. There is no flare. There is no response. There is no gas to map. The technique simply does not apply. Another method used for active systems is gas dynamics, which measures the velocities of gas orbiting close to the black hole and uses those velocities to infer the central mass. This has been applied to a number of nearby galaxies where gas disks around the central black hole can be spatially resolved. But again, a dormant black hole has no gas disk. The gas is gone. That is precisely why the black hole is dormant. The fuel that would allow both feeding and detection has been exhausted or expelled. Every technique that relies on the black hole interacting with surrounding material fails when the material is not there. That leaves gravity alone, not gravity acting on gas because the gas is gone. Gravity acting on the only thing still orbiting the center in sufficient quantities to be measured. Stars. This is why the discovery in MRG M0138 is so significant. The team did not find this black hole by detecting its light. They found it by detecting its gravity, and they did so at a distance where gravity had never been used this way before. The technique is called stellar dynamics, and in principle it is beautifully simple. Every star in a galaxy moves under the influence of gravity. The speed and direction of a star's motion at any given point are determined by the total mass enclosed within its orbit. Stars that orbit closer to the center of a galaxy are responding primarily to the mass concentrated in the core. Stars further out are responding to the cumulative mass of everything inside their wider orbit. If you can measure the velocities of stars at different distances from the center of a galaxy, you can construct a profile of how mass is distributed throughout the system. In practice, this is extraordinarily difficult. You are not watching individual stars move across the sky like watching a bird fly past a window. The motion is measured through spectroscopy, specifically through the Doppler effect. When a star moves toward you, its light shifts slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. The amount of the shift tells you the velocity. By measuring the light from many stars in a particular region of a galaxy, you can determine the average velocity and the spread of velocities, known as the velocity dispersion, in that region. The velocity dispersion is the key quantity. In a galaxy where only stars and gas and dark matter contribute to the central mass, the velocity dispersion rises gradually toward the center. But if a supermassive black hole sits at the core, the velocity dispersion near the center rises sharply. Stars within the black hole's gravitational sphere of influence the region where the black hole's gravity dominates over the galaxy's overall gravitational field, moves significantly faster than stars just outside it. The steeper the rise, the more massive the central object. This is not a new method. Stellar dynamics has been used for decades to weigh supermassive black holes in nearby galaxies. The measurement of Sagittarius A star at the center of our Milky Way is the most famous example. In that case, astronomers tracked individual stars orbiting the galactic center for more than 20 years, mapping out complete orbital paths and deriving a mass of approximately 4 million solar masses with extraordinary precision. But Sagittarius I star is close. 26,000 light-years is practically next door in cosmic terms. The stars around it can be resolved individually using adaptive optics on large ground-based telescopes. At greater distances, individual stars blur together. The technique transitions from tracking individual orbital paths to measuring the collective velocity dispersion of unresolved stellar populations. This works, but it becomes progressively harder as distance increases because the region you need to resolve, the sphere of influence of the black hole, becomes smaller and smaller in angular size on the sky. Before this study, the farthest distance at which stellar dynamics had been used to weigh a dormant supermassive black hole was approximately 700 million light-years. That was already near the edge of what existing telescopes could accomplish. MRG M0138 sits at a distance that dwarfs that previous limit so completely that no one expected the technique to work there. Under normal circumstances, measuring stellar dynamics at a distance of more than 10 billion light-years would be flatly impossible. The black hole's sphere of influence, the region where its gravity dominates, would subtend an angle on the sky so vanishingly small that no telescope could resolve it. This is where gravitational lensing transforms the problem. The massive foreground galaxy cluster does not just amplify the brightness of MRG M0138, it amplifies the angular size. The galaxy appears approximately 30 times larger than it would without lensing. Structures that would normally be far too small to resolve are stretched across a wider patch of sky. The black hole's sphere of influence, which would be an impossibly tiny dot without lensing, becomes large enough for Webb's near-infrared spectrograph to map. But lensing does not simply enlarge the image the way a magnifying glass enlarges a page of text. It distorts it. The curvature of space around the foreground cluster stretches and warps the image of the background galaxy in complex, non-uniform ways. Different parts of the galaxy are magnified by different amounts. The shape is sheared. Straight lines become curves. The spatial relationship between one part of the galaxy and another is altered by the geometry of the lens. This matters enormously for stellar dynamics. The entire technique depends on knowing the precise position of each measurement relative to the center of the galaxy. You need to know exactly how far a given star population is from the core in order to interpret its velocity correctly. If the lens model is wrong, if it places a measurement at the wrong physical distance from the center, the velocity profile is distorted. A small error in the lens reconstruction can produce a large error in the mass estimate. An inaccurate model could make an ordinary galaxy look like it harbors a massive black hole, or, equally dangerously, make a real black hole signature disappear into noise. The team had to build an extremely precise model of the gravitational lens itself before they could analyze the galaxy behind it. This required mapping the mass distribution of the foreground cluster, accounting for both the visible galaxies within it and the much larger contribution of invisible dark matter that provides the bulk of the cluster's gravitational effect. They use the positions, shapes, and magnifications of multiple lensed images, not just MRG M0138, but other background galaxies lensed by the same cluster, to constrain the model. The result was a detailed map of how space was curved in the region of the cluster, allowing them to reverse the distortion and reconstruct what MRG M0138 would look like without the lens. Only after that reconstruction was complete could the stellar dynamics analysis begin. Every velocity measurement had to be mapped back through the lens model to its true position within the galaxy. The uncertainties in the lens model had to be propagated through the dynamical analysis and reflected in the final mass estimate. This is not a simple task. It is a chain of precision, each link dependent on the one before it, stretching from the raw photons collected by Webb all the way to the final number, 6 billion solar masses. The fact that the chain held, that the measurement survived every test and every source of systematic error the team could identify, is a testament to how carefully this work was done. The near-infrared spectrograph, built by the European Space Agency as one of the 4 primary science instruments aboard Webb, has a mode called the integral field unit. This mode does not just take a single spectrum of a single point in the sky. It takes spectra simultaneously across a 2-dimensional patch, producing a map where every pixel contains a full spectrum. For MRGM0138, this meant the team could extract velocity information at multiple positions across the magnified image of the galaxy. They could measure the velocity dispersion in the core and at increasing distances from the core. They could construct the profile that stellar dynamics requires. The data told a clear story. Near the center of MRG M0138, the velocity dispersion was significantly elevated. Stars in the innermost regions were moving faster than the galaxy's overall mass distribution could explain. The rise was sharp, it was concentrated, and it was centered on a compact region where no visible source of mass existed. The team modeled the galaxy's mass distribution, accounting for the mass contributed by the visible stars and by the expected dark matter halo. They then introduced a central point mass, an unseen object whose gravity would boost the velocities of nearby stars by exactly the amount observed. The best fit model converged on a central mass of approximately 6 billion solar masses. 6 billion times the mass of our star. That phrase needs to be held carefully because the human brain is not equipped to process it intuitively. Let me try to give it shape. Our Sun is a fairly ordinary star. It accounts for 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust orbiting it adds up to barely more than a rounding error compared to the star at the center. The Sun contains enough mass that if you could dismantle it and rebuild it as Earth's, you would get roughly 330,000 of them. Now, take that entire mass, every atom of hydrogen and helium fusing in the core, every particle of the radiative zone, every convective cell churning in the outer layers, the whole thing, and multiply it by 6 billion. That is what is sitting at the center of MRG M0138. An object with 6 billion solar masses that does not produce a single photon of its own, that does not glow, that does not shine, that does not register on any detector tuned to any wavelength of electromagnetic radiation. The only evidence it exists is the motion of the stars caught in its gravitational grip. Stars that have no choice but to accelerate as they pass close. pulled by a curvature in space-time that nothing can see, but everything can feel. It may help to understand the scale by comparison. The supermassive black hole at the center of our Milky Way, Sagittarius A-Weigt star, has a mass of approximately 4 million suns. It is considered a relatively modest example as supermassive black holes go. The black hole at the center of M87, the galaxy famously imaged by the Event Horizon Telescope collaboration in 2019, has a mass of approximately 6.5 billion solar masses. That black hole was actively feeding enough to produce a visible shadow against the glow of superheated gas. The black hole in MRG M0138 is comparable in mass to the one in M87. Roughly the same class of object, roughly the same gravitational footprint, but there is a critical difference. The M87 black hole was detected precisely because it was active enough to heat the gas around it. It had an accretion flow. It had a relativistic jet blasting material outward at nearly the speed of light. It was loud. The black hole in MRG M0138 has none of that. No jet, no heated gas, no accretion glow. It has the same mass as one of the most famous actively feeding black holes in the nearby universe, and yet it produces nothing. This contrast gets at something fundamental about how we have understood the black hole population of the cosmos until now. Our view has been skewed. We see the active ones because they are bright. We catalogue the feeding ones because they announce themselves. And we build our models of black hole growth and galaxy evolution around the objects we can detect. The dormant ones, which may vastly outnumber the active ones at any given moment, have been largely absent from the story. Consider the numbers. In the nearby universe, astronomers estimate that most large galaxies harbour supermassive black holes at their centres. Our Milky Way has one. The Andromeda Galaxy has one. Virtually every massive galaxy examined closely enough has revealed one. But the vast majority of these black holes are not actively feeding. They are dormant. They sit quietly. Their accretion rate's too low to produce significant radiation. They are, in a very real sense, invisible engines, massive objects whose presence can only be confirmed through gravitational effects on their surroundings. In the nearby universe, this is manageable. The galaxies are close enough that stellar dynamics and other gravitational techniques can be applied. Astronomers have weighed dormant black holes in dozens of nearby galaxies by studying the orbits and velocity dispersions of stars near the center. The catalogue is growing, but in the early universe, at distances of billions of light years, these techniques had never been successfully applied to a dormant black hole before. Every supermassive black hole weighed at cosmological distances prior to this study was an active one. A quasar. An object that gave itself away through light. The quiet ones were simply out of reach. This is what makes the MRGM0138 result a qualitative breakthrough, and not merely an incremental one. It is not just that the team measured a black hole at a record distance. It is that they measured a dormant black hole at a cosmological distance for the first time. They proved that the technique works. That the combination of Webb's infrared spectroscopy and the natural magnification of gravitational lensing can reach back more than 10 billion years in cosmic time and detect an object that emits absolutely nothing. The implications of that proof of concept are enormous. If this technique works for one gravitationally lensed galaxy, it can work for others. The universe contains many massive galaxy clusters, each one capable of acting as a gravitational lens. Behind those clusters scattered across the deep sky, are ancient galaxies, some of them quiescent, some of them still forming stars, each one potentially harboring a dormant supermassive black hole at its center. For the first time, astronomers have a method that can reach those black holes. Not the bright ones, the quiet ones, the ones that have been missing from every census of the early universe. There is one more detail about the measurement itself that deserves attention because it illustrates just how precise this work is. The team did not simply detect elevated velocities near the center and declare a black hole. They had to disentangle the black hole's gravitational effect from every other source of mass in the galaxy. The visible stars themselves contribute to the central mass concentration. The dark matter halo surrounding the galaxy contributes its own gravitational signature. The mass-to-light ratio of the stellar population, which depends on the age and composition of the stars, had to be modeled carefully. Each of these components was included in the dynamical model, and the central point mass was added on top of them. The result was not a rough estimate, it was a constrained measurement with quantified uncertainties, subjected to the standards required for publication in science. One of the most selective peer-reviewed journals in the world. The team tested alternative models. They checked whether the data could be explained without a central black hole, by adjusting the mass-to-light ratio or the dark matter profile. The answer was consistent. The elevated central velocity dispersion required a compact, massive object. The data demanded it. Andrew Newman of Carnegie Science, the lead author of the study, described the significance in direct terms. By combining Webb data with gravitational lensing, the team could peer inside the black hole's sphere of influence, the region where its gravity boosts the speeds of stars. He emphasized that stellar dynamics is one of the most reliable techniques available for weighing a black hole, and that extending it to such an early period in cosmic history was a goal the team had been working toward for years. Richard Ellis of University College London, the study's senior author, framed the result in terms of what it enables going forward. He explained that by demonstrating the feasibility of this technique for galaxies in the early universe, astronomers can now undertake a more complete census of how black holes develop over time and understand their role in shaping how galaxies evolve. That word, census, is critical. Until this measurement, the census of supermassive black holes in the early universe was a census of the noisy ones, the bright ones, the actively feeding ones. Every conclusion drawn about how black holes grew, how they related to their host galaxies, how they influenced the evolution of the structures around them, was based on the subset of black holes that happened to be eating at the time we looked. Now, for the first time, the quiet ones can be included. The dormant ones. The ones that may have already finished the most important chapter of their existence and settled into silence by the time Webb's light reached them. And when you start including the quiet ones, the story of how galaxies and black holes grew together in the early universe changes. Because MRG M0138 is not just a galaxy with a massive black hole. It is a galaxy that has stopped forming stars. It is a galaxy that is dead. And the black hole at its center may not be an innocent bystander in that death. The relationship between the two, between the 6 billion solar mass engine at the center and the silence of the galaxy around it, is where this story turns from a measurement into a mystery. Because astronomers do not believe this is a coincidence. They believe the black hole and the death of the galaxy are connected. They believe the black hole may once have been responsible for the very process that shut the galaxy down. And the mechanism through which it may have done that is one of the most violent processes in the history of the universe. A process that begins with feeding and ends with starvation. A process in which the black hole grows so powerful that it destroys the very environment that created it. That is the story of quasar feedback. And it is the key to understanding why MRGM0138 looks the way it does today, more than 10 billion light years away, faint and red and quiet. A galaxy that may have been murdered by the thing that lived at its center. There is a paradox at the center of MRGM0138 that goes deeper than the invisibility of its black hole. It is a paradox of timing. Here is a galaxy that existed when the universe was only 3 billion years old. At that age, the cosmos was drenched in gas. Hydrogen and helium filled the spaces between galaxies and threaded through them in vast filaments and clouds, constantly falling inward under gravity, feeding the formation of new stars at rates that would be extraordinary by modern standards. Galaxies at that epoch were factories. They were pulling in raw material and converting it into stars at 10, 50, sometimes hundreds of times the rate our Milky Way manages today. The early universe was not a quiet place. It was a furnace. And yet MRGM0138 was already cold. It had already stopped. Its stellar population was old and red, dominated by stars that had formed long before the light Webb captured had even begun its journey. No new stars were being born. No gas was collapsing. No stellar nurseries were glowing. The factory had shut down, while every other factory around it was running at full capacity. Something killed this galaxy. Something cut off its fuel supply, interrupted the process of star formation, and left it drifting as a relic in an era of cosmic productivity. And the leading suspect is the very object sitting at its center. The 6 billion solar mass black hole that is now dormant, silent, and invisible. Because astronomers believe that black hole was not always quiet. They believe it was once one of the most violent objects in the observable universe. They believe it was a quasar, and they believe the energy it released during its feeding phase may have been directly responsible for destroying the conditions that allowed stars to form. This idea is called quasar feedback, and it is one of the most important concepts in modern astrophysics. To understand it, you need to understand what happens when a supermassive black hole feeds. A black hole does not simply swallow matter the way a drain swallows water. Matter falling toward a black hole does not drop straight in. It carries angular momentum, which means it spirals. As the material spirals inward, it forms a flattened, rotating structure around the black hole called an accretion disk. The disk is not peaceful. It is a zone of extreme violence. Material in the inner regions orbits faster than material in the outer regions, creating friction between adjacent layers. That friction generates heat. Enormous heat. The gas in the innermost parts of the accretion disk can reach temperatures of millions of degrees. At those temperatures, the gas radiates furiously. It emits across the electromagnetic spectrum, from radio waves to visible light, to ultraviolet to X-rays. The total energy output can be staggering. At peak luminosity, the accretion disk alone can exceed the combined light of every star in the host galaxy by a factor of 100 or more. That radiation is not merely visible across cosmic distances. It is powerful enough to physically reshape the galaxy that surrounds it. The disk, a compact ring of tortured gas being compressed and heated, as it spirals toward the point of no return, becomes the single most energetic structure in the entire system. But the radiation is only part of the story. Many actively feeding black holes also produce jets. Narrow beams of material accelerated to nearly the speed of light and launched outward from the poles of the accretion disk along the axis of the black hole's spin. These jets can extend for hundreds of thousands of light years, far beyond the boundaries of the host galaxy, punching through the surrounding gas and depositing enormous amounts of energy into the intergalactic medium. The mechanism that produces the jets involves the interaction between the rotating black hole, the magnetic fields threading the accretion disk, and the geometry of space-time near the event horizon. The details are still being refined, but the jets themselves are observed directly in many active galaxies. If you could have watched MRG M0138 during its quasar phase, what you would have seen would bear no resemblance to the quiet fossil web observed. The center of the galaxy would have been blazing. The accretion disk around the black hole, perhaps only a few light days across, would have been the most luminous structure in the entire system, despite occupying a volume vanishingly small compared to the galaxy surrounding it. From a distance, the galaxy's core would have appeared as a single brilliant point, so bright that the surrounding stars were invisible against its glare. That point would have been visible across billions of light years, a beacon marking the location of one of the most energetic sustained processes in the known universe. The light from that quasar would not have been gentle. At close range, the radiation field would have been intense enough to ionize atoms, strip electrons from gas molecules, and drive temperatures in the surrounding interstellar medium to millions of degrees. Gas clouds that had been slowly cooling and condensing toward collapse. The clouds that would otherwise have become the next generation of stars would have been flash heated into a diffuse, superheated plasma incapable of gravitational contraction. The nurseries were not merely disrupted, they were sterilized, and that was only the radiative component. If the quasar also produced jets, as many of this luminosity class do, the mechanical impact would have been equally devastating. Narrow beams of relativistic plasma, traveling at close to the speed of light, would have drilled through the galaxy's interstellar medium like blowtorches through fog. Where the jets impacted denser gas, they would have created expanding shock fronts, walls of compressed, superheated material that rolled outward through the galaxy at thousands of kilometers per second. The shocks would have swept up gas, heated it, and in many cases driven it entirely out of the galaxy's gravitational well, expelling raw material into the intergalactic void where it could no longer contribute to star formation. This phase would not have lasted forever. Estimates for the duration of a major quasar episode range from tens of millions to a few 100 million years. In cosmic terms, that is brief, but the damage would have been total. By the time the quasar faded, by the time the accretion rate dropped, and the disk cooled and the jets sputtered out, the galaxy would have been transformed. Its gas reserves would have been depleted, expelled, or heated beyond usability. The raw material for star formation would be gone, and the galaxy would begin its long, irreversible slide into quiescence. The quasar was the brightest thing in the galaxy's history, and its legacy was silence. Now combine these two outputs: radiation flooding outward in all directions from the accretion disk, jets blasting material at relativistic speeds along specific axes, Together they represent an energy source at the center of a galaxy that is capable of affecting the entire system around it. And here is the critical point. That energy does not just escape into the void. It interacts with the gas in the galaxy. The gas that is the raw material for forming new stars. The interaction takes several forms, and each one pushes in the same direction. Radiation pressure is the most direct. Photons carry momentum. When the accretion disk radiates at full power, the photon flux near the center of the galaxy is intense enough to physically push gas outward. The radiation presses against the gas clouds like a wind pressing against a sail. If the luminosity is high enough, the radiation pressure can exceed the gravitational pull, trying to hold the gas in place. The gas gets driven outward, expelled from the central regions of the galaxy, and in some cases blown entirely out of the system. Mechanical feedback from the jets adds another layer. The jets do not just pass through the surrounding gas cleanly, they slam into it. They create shock waves that propagate outward through the galactic medium, compressing some gas and heating the rest. The heating is particularly destructive to future star formation. Star formation requires gas that is cold and dense enough to collapse under its own gravity. Hot gas does not collapse, it expands. It resists the gravitational contraction that would otherwise pull it together into new stellar cores. By heating the gas throughout the galaxy, the jets effectively sterilize the environment. The raw material for star formation is still technically present, but it is too hot to use. There is a third mechanism that operates on larger scales. The energy deposited into the gas surrounding the galaxy, the circumgalactic medium, can prevent new gas from falling in. Galaxies do not just use the gas they were born with. They continuously accrete fresh gas from the cosmic web, the network of filaments that threads through the large-scale structure of the universe. This ongoing supply of cool, fresh gas is what sustains star formation over billions of years. If the energy from a quasar heats the circumgalactic medium enough, it can shut off this supply line. The fresh gas that would normally cool and fall inward is kept at temperatures too high to condense. The galaxy is cut off from its fuel source. Even after the quasar eventually fades, the galaxy has no new gas to work with. Star formation does not just slow, it stops. Each of these mechanisms has been observed directly in active galaxies in the nearby and distant universe. Outflows of gas driven by radiation pressure have been measured in numerous quasar systems, sometimes moving at speeds of thousands of kilometers per second. Jets have been observed heating the gas in galaxy clusters, preventing the hot intracluster medium from cooling and forming stars. Simulations of galaxy evolution that include quasar feedback produce results that match the observed properties of real galaxies far better than simulations that leave it out. This is not a speculative idea. It is a cornerstone of the current theoretical framework for galaxy evolution. Without quasar feedback, simulations produce galaxies that are far too massive and far too star-rich compared to what we observe. The feedback from supermassive black holes is required to explain why the most massive galaxies in the universe stopped growing when they did. It is the break in the system, the mechanism that turns off the engine. And this is where MRG M0138 becomes so important, because it appears to be a galaxy where this entire process has already played out. The black hole grew, it fed voraciously, it became a quasar, it poured energy into its surroundings, driving gas outward, heating what remained, cutting off the supply of fresh material. Star formation slowed and then ceased. The galaxy went quiet. And then the black hole itself, starved of the gas that had been fueling it, went quiet too. The accretion disk thinned and cooled. The jets faded. The radiation dropped to negligible levels. The quasar shut down. What remains is what Webb observed: a dead galaxy with an invisible black hole at its center. A system where the most violent chapter of its history is already over. A relic of a process that began with growth and ended with destruction and silence. Now, it is essential to state clearly what is confirmed and what is inferred here. The mass of the black hole is measured. 6 billion solar masses, derived from stellar dynamics with quantified uncertainties, published in the journal Science. The quiescence of the galaxy is confirmed. Webb's spectra show no signs of ongoing star formation. The presence of an old stellar population dominated by red, aging stars is confirmed. What is not confirmed, and must be presented honestly, is the causal link between the black hole's past activity and the galaxy's current silence. Researchers believe, based on the theoretical framework and on observations of similar systems, that MRGM0138 probably once hosted a powerful quasar. They believe the energy released during that quasar phase probably contributed to the shutdown of star formation, but the word probably is doing important work in that sentence. The quasar phase itself is not directly observed. It happened in the past. Before the era we are seeing in Webb's image, the evidence is circumstantial, consistent with the theoretical picture, supported by simulations, but not directly witnessed. This distinction matters because science operates on the difference between what is shown and what is suggested. The Newman team's paper in Science is careful about this. They present the dormant black hole as a measured fact. They present the quiescent state of the galaxy as a measured fact. They discuss the probable connection to a past quasar phase as a leading interpretation supported by the broader body of evidence. They do not claim to have watched the black hole kill the galaxy. They claim to have found the crime scene and identified the most likely suspect. And the suspect's profile is compelling. A black hole of 6 billion solar masses does not grow to that size passively. It does not accumulate that much mass by quietly sitting in the center of a galaxy and waiting for material to drift in. At some point in its history, this black hole was almost certainly feeding at enormous rates. It was consuming gas in quantities sufficient to power one of the most luminous types of objects in the universe. The energy it released during that growth phase would have been immense, more than enough to disrupt the gas supply of its host galaxy through the mechanisms described above. The timing also fits. MRGM0138 is observed when the universe was about 3 billion years old, and the galaxy had already stopped forming stars by that point. The quasar phase, if it occurred, would have happened even earlier, perhaps when the universe was between 1 and 2 billion years old. That is exactly the epoch when quasar activity in the universe was at or near its peak. The early cosmos was rich with gas, feeding rates were high, and supermassive black holes were growing rapidly. A black hole that reached 6 billion solar masses by the time the universe was 3 billion years old must have undergone its most intense growth during that earlier window. The scenario is not just plausible, it is almost required by the numbers. There is a broader context that makes this finding even more significant. For decades, astronomers studying galaxies in the nearby universe have noticed a tight relationship between the mass of the central supermassive black hole and the properties of the host galaxy. The relationship was first clearly established in the year 2000, when two independent teams published papers demonstrating that the mass of a galaxy's central black hole correlates tightly with the velocity dispersion of the stars in the galaxy's central bulge. This became known as the M-sigma relation. The correlation is remarkably tight, spanning several orders of magnitude in black hole mass. Galaxies with more massive bulges, where the stars move faster on average, systematically harbor more massive central black holes. Galaxies with smaller, slower bulges harbor smaller ones. The scatter around the relationship is small enough that measuring the velocity dispersion of a galaxy's bulge allows you to predict the mass of its central black hole with surprising accuracy, even without directly measuring the black hole at all. This was not expected. The black hole, no matter how massive, occupies a region that is vanishingly small compared to the galaxy around it. Its gravitational influence extends only to the innermost fraction of the galaxy's total volume. There is no obvious physical reason why the properties of stars tens of thousands of light years away from the black hole should correlate so precisely with the black hole's mass. The stars in the outer bulge have never been close enough to the black hole to feel its gravity directly. They have never orbited it. They have never been affected by it in any individual sense. And yet, statistically, across galaxy after galaxy, the relationship holds. The most natural explanation is that something regulated the growth of both the black hole and the galaxy's stellar bulge simultaneously. Something that linked the two systems despite the vast difference in their physical scales. And the leading candidate for that linking mechanism is feedback. The black hole grew by feeding on gas. The energy it released during feeding affected the gas supply of the entire galaxy. The galaxy's ability to form stars was constrained by the black hole's energy output, and the black hole's ability to keep feeding was constrained by the depletion of gas that its own feedback caused. The result is a mutual throttle, a self-regulating loop that drives both systems toward a predictable ratio, locking the black hole mass and the galaxy properties into the tight correlation we observe. The feedback loop described above does not just link the two systems during their growth, it drives them toward a shared endpoint. As the black hole grows more massive and its energy output intensifies, it progressively suppresses the galaxy's ability to form new stars. Eventually, the feedback becomes powerful enough to shut everything down, cutting off both the galaxy's star formation and the black hole's own fuel supply at roughly the same time. What matters for this story is how the endpoint differs depending on the strength of the engine at the center. A more massive black hole produces stronger feedback. Stronger feedback shuts down star formation sooner. And a galaxy that stops forming stars sooner ends up with a smaller stellar population relative to its central engine. The implication is that the final properties of a galaxy are not determined by its gas supply alone. They are shaped, constrained, and in some cases dictated by the mass of the black hole that grew alongside it. This relationship has been well established in the nearby universe, but testing whether it existed in the early universe, when galaxies and black holes were still in their most active growth phases, has been extraordinarily difficult. The problem is exactly the one described earlier. In the early universe, the only black holes we could weigh were the active ones, the quasars. And quasars are by definition in the middle of their growth. They are feeding. They are not yet in equilibrium. Measuring the black hole to galaxy mass relationship for quasars tells you about the ratio during the growth phase, not after it. MRG M0138 is different. The growth phase is over. The black hole has stopped feeding. The galaxy has stopped forming stars. Both have settled. This is the first time astronomers can measure the black hole mass and the galaxy properties of a system in the early universe that has already reached its endpoint. It is the first chance to test whether the relationship between black hole mass and galaxy properties that holds in the nearby universe was already in place more than 10 billion years ago. The early results suggest it was. The 6 billion solar mass black hole sits inside a galaxy whose stellar mass and density are consistent with the scaling relations observed locally. The ratio of black hole mass to galaxy properties falls within the range established by nearby galaxies. This does not prove that the feedback loop was responsible, but it is consistent with the idea that the same regulatory mechanism was already operating when the universe was a fraction of its current age. That finding has profound implications for models of cosmic evolution. It means the co-evolution of black holes and galaxies is not a late development. It is not something that emerged gradually over billions of years as galaxies matured. It was already in place during the first few billion years of cosmic history. The feedback loop was already functioning. Black holes were already shaping the destinies of their host galaxies. Galaxies were already being regulated, constrained, and in some cases killed by the objects at their centers. And this feeds directly into one of the most active questions in all of extragalactic astronomy. How do galaxies die? The term astronomers use is quenching. A galaxy is quenched when it stops forming stars permanently. Not a temporary pause, not a lull between episodes of activity. A full shutdown that the galaxy never recovers from. Quenched galaxies are common in the modern universe. Many of the most massive galaxies we see today, particularly the giant elliptical galaxies that sit at the centers of galaxy clusters, are quenched. They are filled with old red stars and show no signs of new ones being formed. Understanding how and when galaxies quench is one of the central problems of modern astrophysics. Quasar feedback is one of the primary proposed mechanisms, but it is not the only one. Other processes can also suppress star formation. The exhaustion of gas through normal star formation, the strip-in of gas by environmental effects in dense galaxy clusters, the heating of gas by virial shocks as it falls into massive dark matter halos, all of these can contribute. The question is which mechanism dominates, and under what conditions, and at what cosmic epoch. MRG M0138 provides a data point in that debate. It is a galaxy that quenched early, very early, when the universe was barely 3 billion years old. That early quenching is difficult to explain without a rapid and powerful energy injection. Environmental stripping requires a dense cluster environment. Simple gas exhaustion requires more time than was available. The most natural explanation, given the massive dormant black hole at the center, is that quasar feedback played a major role. But the team is not stopping with a single galaxy. Newman and his colleagues are already analyzing Webb observations of 4 additional distant galaxies that are also gravitationally lensed and also appear to have undergone some form of quenching. These 4 galaxies were selected because each one sits behind a massive foreground cluster that provides sufficient magnification for stellar dynamics measurements. Each one shows evidence of reduced or halted star formation, But critically, they did not all quench at the same time. Some of them still show traces of relatively recent stellar populations, indicating that their star formation shut down later than in MRG M0138. Others appear to be in transitional states, galaxies where star formation has slowed dramatically but may not have fully ceased at the epoch when Webb observed them. This staggered timeline is scientifically valuable in a way that a single snapshot cannot be. If the team can measure the black hole masses in each of these galaxies and compare them to the quenching timelines, they can begin to reconstruct the sequence of events. Did the black holes grow first and then quench their galaxies? Or did the black holes and the galaxies shut down at roughly the same time, suggesting a more synchronized process? Is there a threshold black hole mass above which quenching becomes rapid and total, and below which it is slow and partial? Does the relationship between black hole mass and galaxy death hold consistently across different environments and different cosmic epochs? Or does it break down under certain conditions? Each of these questions requires multiple data points, and the 4 additional galaxies are the first steps toward building that sample. Newman has noted that the stellar populations in these galaxies are younger than those in MRG M0138, meaning star formation continued longer before shutting down. This raises the possibility that the feedback process operates on different timescales depending on conditions. Perhaps the mass of the black hole, perhaps the gas density of the galaxy, perhaps the rate at which fresh gas was being supplied from the cosmic web. By comparing the complete picture across all 5 galaxies, the team can begin to test which variables matter most and how sensitive the quenching process is to each one. The diversity within this small sample is precisely what makes it powerful. Rather than a single snapshot of one outcome, the team will have a sequence of scenes from different moments in the shutdown process, each one constraining the theoretical models in a different way. This is where the discovery transforms from a single remarkable measurement into the foundation of a new observational program. The technique has been proven. Stellar dynamics at cosmological distances, enabled by gravitational lensing and Webb's infrared spectroscopy, is now a demonstrated capability. Every massive galaxy cluster in the sky is a potential lens. Behind every lens, there may be ancient galaxies with dormant black holes, whose masses can now be measured for the first time. The tools to expand this work are either already operational or on the way. The Euclid satellite, launched by the European Space Agency, is conducting a wide field survey that will discover vast numbers of gravitationally lensed galaxies across the sky, and each one is a potential target. The Nancy Grace Roman Space Telescope, scheduled by NASA, will add even more lens systems to the catalogue. And the giant Magellan Telescope, currently under construction at Carnegie Science's Las Campanas Observatory in Chile, will have the angular resolution and spectroscopic power to study the motions of stars in distant galaxies at a level of detail that exceeds even Webb's capabilities. Within the next decade, astronomers may have not just one dormant black hole mass from the early universe, but dozens, perhaps hundreds. Enough to build a statistical picture of how common these massive dormant engines are, how their masses relate to their host galaxies, and how the shutdown process varied across different types of galaxies and different cosmic environments. That statistical picture will answer questions that a single measurement cannot. Is MRGM 0138 typical? are most massive early galaxies that quenched early harboring black holes of similar scale? Or is it an outlier, an unusually extreme case? Do smaller dormant black holes exist in galaxies that quenched later or less completely? Is there a threshold mass above which feedback becomes inevitable? A tipping point beyond which the black hole guarantees the death of its host? These are not rhetorical questions. They are the active research frontier, and for the first time, the observational tools exist to pursue them. There is one more dimension of this story that connects the MRG M0138 result to the larger picture of what Webb has been finding across the early universe. In the years since its launch in late 2021, Webb has repeatedly discovered objects in the early cosmos that challenged expectations. Galaxies that were too massive for their age, black holes that were too large to have grown through conventional means, structures that appeared more evolved and more complex than models predicted for such an early epoch. MRG M0138 fits into that pattern. A 6 billion solar mass dormant black hole inside a quenched galaxy at redshift 2, observed when the universe was only 3 billion years old, is another example of the early cosmos producing extreme outcomes faster than the models anticipated. The growth required to build a black hole that massive in that time frame pushes against the limits of standard accretion models. The quenching required to shut down star formation that early pushes against the limits of standard galaxy evolution models. Both findings suggest that the processes governing the growth of black holes and the death of galaxies in the early universe were faster, more efficient, and more violent than the theoretical frameworks built on nearby observations had predicted. This does not mean the models are wrong in their fundamental physics. It means the conditions in the early universe allow those physics to operate at extremes that are rare or non-existent in the modern cosmos. The gas densities were higher, the merger rates were higher, the gravitational interactions were more frequent and more intense. Black holes had access to more fuel and fewer constraints. Feedback events were more powerful and more consequential. The early universe was, in every meaningful sense, a more violent place. And MRG M0138 is a fossil of that violence. A galaxy that was built fast, burned hard, and shut down early, leaving behind a dead stellar population and an invisible engine that will sit in silence for the rest of cosmic time. The question that remains, the one that this single galaxy cannot answer by itself, is how many other fossils are out there? How many ancient dead galaxies across the observable universe are carrying dormant black holes at their centers that no survey has ever detected? How many quiet images in the archives of Webb, Hubble, and every other telescope are hiding the gravitational fingerprints of objects that shaped the history of their host galaxies and then went silent? The answer to that question is what the next generation of observations will pursue. And the answer may fundamentally change our understanding of how the universe assembled its most massive structures. Because if dormant black holes of this scale are common in the early universe, it means the loudest objects we have been studying, the quasars, are only half the story. The other half is written in silence, in galaxies that look dead and faint and unremarkable, in images that most people would scroll past without a second thought. The most important thing in the image is the thing you cannot see. And for the first time, science has the tools to look for it. For as long as humans have studied the sky, we have built our understanding of the universe around one assumption so fundamental that it barely registers as an assumption at all. We assumed that the most important objects are the ones we can see. The brightest star must be the nearest or the largest. The most luminous galaxy must be the most massive. The most powerful black hole must be the one blazing with the light of superheated gas falling past the point of no return. Light has been our compass. Brightness has been our hierarchy. And for most of the history of astronomy, that instinct served us well. Stars that burned brighter really were more massive. Galaxies that glowed more fiercely really were forming more stars. Quasars that outshone their host galaxies really were powered by some of the most massive black holes in the cosmos. But MRG M0138 reveals the limit of that instinct. It reveals a category of object that violates the assumption so completely that it forces a reconsideration of how we inventory the universe. Because the most massive black hole ever measured at cosmological distance using stellar dynamics is not a bright one. It is not an active one. It is not surrounded by glowing gas or producing relativistic jets or radiating enough energy to outshine a trillion suns. It is dark. It is quiet. It is dormant. And it was found not because it announced itself, but because the stars around it could not help betraying its presence through their motion. This is a conceptual turning point, and it extends far beyond a single galaxy or a single black hole. It touches the way we understand the entire population of supermassive black holes across cosmic history. For decades, the study of supermassive black holes in the early universe has been dominated by quasars. These brilliant objects, powered by actively feeding black holes, were the first extragalactic sources identified at cosmological distances. They are easy to find, their light is unmistakable, and they have provided an extraordinary wealth of data about the conditions in the early cosmos. Quasar surveys have catalogued thousands of actively feeding black holes across a range of redshifts, building a picture of when black hole growth was most intense, how rapidly black holes could accumulate mass, and how their activity correlated with the properties of their host galaxies. But that picture is incomplete. It's like studying the history of a civilization by reading only the records of its wars. The battles are dramatic. They are well documented. They produce clear evidence that survives across time. But they do not tell you about the periods of peace, the long stretches of quiet productivity and slow change that make up the majority of a civilization's existence. The wars are the exceptions. The peace is the norm. And if you only study the wars, you fundamentally misunderstand the civilization. Quasars are the wars. They are the brief, violent episodes in the life of a supermassive black hole when conditions align to produce spectacular energy output. But those episodes do not last. They cannot last. The fuel supply is finite. The feedback mechanisms described earlier actively work to shut down the feeding process. A quasar phase might last tens of millions of years, perhaps a few 100 million in extreme cases. After that, the gas is depleted, the accretion rate drops, the luminosity fades, and the black hole goes dormant for the rest of the galaxy's existence, which could span billions of years. The black hole sits quietly at the center, still massive, still warping space-time, still influencing the orbits of every star within its gravitational reach, but producing no light, generating no signal, contributing nothing to the electromagnetic census of the universe. If the quasar phase is brief and the dormant phase is long, then at any given moment in cosmic history, the majority of supermassive black holes should be dormant. The active ones, the quasars, should be the minority. The quiet ones should vastly outnumber them, and yet our catalogues are filled with the active ones, and nearly empty of the quiet ones, at least for the early universe. The reason is obvious. We could not see the quiet ones. We had no method sensitive enough to detect them at billions of light years. Until now. The MRG M0138 measurement does not just add one black hole to the ledger. It opens a door. It demonstrates that the dormant population, the dark majority, the unseen engines scattered throughout ancient galaxies across the observable universe, can now be found. Not easily, not cheaply. The technique requires gravitational lensing, Webb-class infrared spectroscopy, careful dynamical modeling, and significant telescope time. But it works. And that changes the nature of the question. Before this result, the question was whether dormant supermassive black holes exist in the early universe. The answer was almost certainly yes, based on theory and on what we know about black hole life cycles, but there was no direct evidence. The dormant population was a theoretical necessity, not an observational fact. After this result, the question shifts. The dormant population is confirmed to exist. The question now is how large it is, how its properties distribute, and what it tells us about the full history of black hole growth that the quasar surveys alone could never reveal. This is not just an academic exercise. The answers have consequences for some of the biggest open problems in astrophysics. Consider the question of black hole seeds. One of the most pressing mysteries in the study of supermassive black holes is how they got so massive so quickly. Webb has repeatedly found supermassive black holes in the early universe that are too massive to have grown through standard accretion processes alone, given the time available since the Big Bang. Several theories have been proposed to explain this. Perhaps the seed black holes that formed in the early universe were already much larger than the stellar mass black holes produced by collapsing stars. Perhaps direct collapse of massive gas clouds produced intermediate mass seeds that could grow more quickly. Perhaps super Eddington accretion, feeding beyond the theoretical maximum rate, was more common in the early cosmos than previously thought. Each of these theories makes different predictions about the total population of supermassive black holes, including the dormant ones. If massive seeds were common, there should be many dormant black holes in early galaxies that never reached quasar luminosity, but still grew to substantial sizes. If super Eddington accretion was the dominant growth mechanism, the dormant population might show a specific distribution of masses that reflects the physics of extreme feeding. Measuring the dormant population directly would provide constraints that quasar surveys alone cannot offer. There is another dimension that connects directly to what we discussed about galaxy quenching. If quasar feedback is the primary mechanism that kills massive galaxies, then every quenched galaxy in the early universe should harbor a dormant black hole massive enough to have generated sufficient feedback. The mass required depends on the details of the feedback model, but it can be estimated. By measuring the black hole masses in a sample of quenched early galaxies, astronomers can test whether the feedback models produce the right numbers. If the black holes are consistently massive enough to explain the quenching, the models are supported. If some quenched galaxies harbor black holes that are too small to have produced the necessary feedback, then other quenching mechanisms must have been involved. MRG M0138 With its 6 billion solar masses in a galaxy that quenched when the universe was roughly 3 billion years old, is consistent with the feedback picture. The black hole is more than massive enough, but one data point does not make a trend. The 4 additional galaxies that Newman and his colleagues are currently analyzing with Webb will provide the first steps toward that trend. Each of those galaxies quenched at different times, offering a timeline of when and how the shutdown process occurred. If the black hole masses in those galaxies follow a pattern correlating with the quenching timescale or the galaxy properties, the evidence for feedback as the dominant mechanism will strengthen considerably. There is one more question embedded in this research program that has not been discussed yet, and it adds a final unsettling dimension to the story. The team has stated explicitly that future observations will not only seek to understand how dormant black holes help shut down their galaxies, but also how dormant black holes can reactivate when large amounts of matter begin flowing into them again. This is a distinction that matters. A dormant black hole is not a dead black hole. It has not lost any of its mass. It has not decayed. It has not weakened. The event horizon is still there, the same size it was when the quasar phase ended, defined by the same 6 billion solar masses of enclosed gravity. The machinery of destruction has not been dismantled. It has simply been idled. The engine is intact. What is missing is the fuel, and fuel can return. The universe is not static. Galaxies do not drift in permanent isolation. They interact. They collide. They merge. When 2 galaxies fall toward each other under gravity and eventually combine, the merger can deliver enormous quantities of fresh gas to the central regions of the resulting system. Gas that was spread across the outskirts of both galaxies gets funneled inward by gravitational torques during the collision. It piles up in the core, and if that gas reaches the vicinity of a dormant supermassive black hole, the feeding can begin again. The accretion disk reforms. The gas heats up. The radiation returns. The jets may reignite. A black hole that had been silent for billions of years can, in the space of a few million years, reawaken as a quasar and begin pouring energy back into its surroundings. The galaxy that had been quietly aging, slowly fading, drifting through the cosmos as a collection of old stars, is suddenly flooded with radiation from its own center. The feedback process can restart. The cycle of growth, destruction, and silence can play out a second time. This is not theoretical speculation. Astronomers have observed reactivated black holes in the nearby universe, galaxies that show clear signs of a recent merger event, sometimes display renewed nuclear activity at their centers. A fresh accretion episode triggered by the inflow of gas from the collision. The timescales vary. Some reactivations are brief and modest, others are powerful enough to qualify as full quasar episodes. The dormant phase in these cases was not a permanent retirement. It was an intermission. Whether the black hole in MRG M0138 will ever reactivate depends on what happens to its host galaxy over the next several billion years. If it remains isolated, if no gas-rich galaxy falls into its gravitational path, the black hole will stay dormant indefinitely. It will sit in silence for the rest of cosmic time, slowly losing mass through Hawking radiation on a timescale so long that it dwarfs the current age of the universe by factors that have no meaningful analogy. But if a merger occurs, if the right collision delivers the right amount of gas to the right place, the 6 billion solar mass engine could start again. The silence would break, and the galaxy that looked dead would once again contain one of the most violent objects in the observable universe. This possibility does not change the scientific conclusions of the current study. It changes the emotional weight of the image. The dormant black hole in MRGM0138 is not a relic in the way that a fossil is a relic. A fossil is the remains of something that can never live again. This black hole is more like a dormant volcano. The magma chamber is still full. The pressure has not been released. The eruption is over for now. But the geology has not changed. The conditions that produced the last eruption could, given the right trigger, produce another. The telescopes and survey missions now coming online, the same instruments described earlier in this story, will multiply the number of lens targets available for this technique by orders of magnitude over the next decade. What was accomplished for one galaxy with extraordinary effort will become routine for dozens, then hundreds. And as the sample grows, the picture that emerges will not be a collection of individual curiosities. It will be something far more consequential. A map of the invisible gravitational architecture that shaped the galaxies we see today. Built not from light, but from the motion of the stars responding to masses that no instrument can see directly. Within the next 10 to 15 years, astronomers may have a catalogue of dormant supermassive black hole masses spanning the first few billion years of cosmic history. That catalogue would represent something genuinely new, a census not of the bright and the loud, but of the dark and the silent. And it would carry a profound implication. Every massive galaxy that exists in the modern universe, including our own, went through some version of this process. A black hole grew at the center. It influenced the evolution of the galaxy around it. At some point, the balance between growth and feedback determined the final properties of both. The end state, the quiet, settled galaxy with a dormant black hole at its heart, is the norm. What we are seeing in MRGM0138 is that norm at its moment of establishment, more than 10 billion years ago. There is something else that deserves careful attention. Something that connects the specific discovery in MRGM0138 to a broader pattern in what Webb has revealed about the early universe since its launch. One of the most consistent themes across Webb's early science results is that the early universe was more mature than expected. Galaxies were more massive, black holes were more grown, structures were more evolved, chemistry was more advanced. At nearly every frontier where Webb has pushed our observational reach deeper into cosmic history, the findings have pushed back against the assumption that the early universe was simple, primitive, and still assembling itself. MRGM0138 is perhaps the most striking example of this pattern. It is not just a massive galaxy observed early in cosmic history. It is a massive galaxy that had already finished its active life. It had already built its stars. It had already grown its black hole. It had already undergone and completed the feedback process that shut down its star formation. And all of this happened within the first 3 billion years. The entire life cycle of a major galaxy, from birth through active growth, through quasar feedback, through quenching to dormancy, played out in less than a quarter of the universe's current age. That speed challenges the models, not fatally, not in a way that breaks the underlying physics, but in a way that requires the models to accommodate more efficient, more rapid processes than they previously included. Gas had to collapse faster, stars had to form faster, the black hole had to grow faster, feedback had to act faster, and the galaxy had to respond to that feedback faster. Every step in the sequence operated at or near the extreme end of what physics allows. This raises a question that sits at the boundary of observation and philosophy, a question that this story has been building toward from the opening sentence. What does it mean that the most terrifying thing Webb photographed is not a bright, violent, actively destructive object, but a quiet, dead, ancient galaxy whose most important feature is invisible? The word terrifying in the title is deliberate, but it does not mean what most people assume at first glance. The black hole in MRG M0138 is not coming toward us. It is not going to consume our solar system. It is not a threat to any living thing on Earth. It is more than 10 billion light years away, receding from us as the universe expands. In every practical sense, it is as harmless as a distant star. The terror is not physical. It is conceptual. It is the terror of realizing that the universe contains objects of almost incomprehensible mass that are completely invisible. That a black hole with the mass of 6 billion suns can sit at the center of a galaxy and emit nothing. No light, no heat, no radiation at any wavelength. It can shape the destiny of an entire galaxy, drive the process that kills star formation across a system containing billions of stars, and then go silent, permanently, invisibly. And unless the precise alignment of a gravitational lens happens to magnify its host galaxy, and a telescope sensitive enough to measure the velocities of its surrounding stars happens to be watching, no one would ever know it was there. It is the terror of scale. 6 billion solar masses is not a number the human mind can hold. You can say the words, you can write the figure, but the gap between the symbol and the reality is vast enough to lose yourself in. Our entire solar system, every planet, every moon, every ring, every comet, every grain of dust, adds up to a fraction of one solar mass. The black hole at the center of MRGM0138 contains 6 billion of those. It is a quantity so far beyond human experience that it exists only as an abstraction, a number that maps to nothing in lived reality. It is the terror of time. The light Webb captured from this galaxy has been traveling for more than 10 billion years. When that light began its journey, our sun did not exist. Our planet did not exist. The atoms that make up your body were scattered across multiple star systems that had not yet gone through the supernova explosions that would one day seed the molecular cloud from which our solar system would form. The galaxy you are looking at in this Webb image was already dead before Earth was born. Its black hole was already dormant before the first bacterium appeared in our oceans. The timescales involved dwarf not just human history, but the entire history of life on this planet. And it is the terror of what remains unknown. MRG M0138 was found because of an extraordinary convergence of circumstances. A massive galaxy cluster happened to sit along the line of sight between Webb and the distant galaxy. That cluster happened to produce a magnification factor of roughly 30 times. The most magnified of the 4 lensed images happened to be oriented in a way that allowed Webb's spectrograph to resolve the velocity structure in the core. The team happened to have the expertise, the telescope time, and the analytical tools to extract the dynamical signal. If any one of those conditions had been absent, the black hole would still be sitting there, invisible and unmeasured, hiding inside an image that no one would have reason to examine twice. How many others are hiding? That question has no answer yet, but the statistical reasoning is suggestive. MRG M0138 is not the only massive quiescent galaxy known in the early universe. Surveys have identified numerous others, red, dead, and old, scattered across the deep fields of Webb and Hubble. If even a significant fraction of those galaxies harbour dormant black holes of comparable mass, the total hidden population is enormous. The universe could be filled with quiet galaxies whose centres conceal masses that rival the most extreme objects astronomers have ever measured, and we would have no way of knowing without the specific combination of lensing geometry and spectroscopic capability that this single discovery required. The early universe in this picture was not just a place where galaxies formed and grew. It was a place where galaxies formed, grew, and died, where black holes were built, fed, and then starved, where the most violent processes imaginable, quasar outbursts capable of disrupting the gas supply of an entire galaxy, played out and then fell silent, leaving behind fossils that would drift through cosmic time for billions of years, carrying inside them the record of a catastrophe that no one witnessed and that no light can describe. The image does not show any of that. The image shows a faint red arc, a smear of ancient photons, bent and stretched by gravity, arriving at a mirror, floating in the cold vacuum a million miles from Earth. The image looks quiet, but the gravity is not quiet. The stars in the center of that galaxy are still moving under the influence of something they cannot escape. Something that warped their orbits billions of years ago and has not released its grip. Something that shaped the history of their galaxy, ended its productive life, and then settled into a silence so complete that no instrument in the universe can hear it. The most terrifying thing Webb has ever photographed is not a glowing monster. It is not a violent collision. It is not a jet of plasma screaming across 100,000 light years. It is a quiet picture of an ancient galaxy that has been dead longer than our sun has been alive. A galaxy that looks like nothing special. A galaxy that most people would ignore. And hidden inside it, invisible at every wavelength, detected only through the whisper of stellar motion, amplified by the bending of space itself, is a black hole with a mass of 6 billion suns. It is not shining. It is not feeding. It is not growing. It has already done everything it will ever do. It built itself. It may have killed its galaxy, and now it waits. Not for anything in particular. Not with intent or awareness or purpose. It simply persists. A concentration of gravity so extreme that it warped the fate of billions of stars, silenced an entire galaxy, and then disappeared from every instrument in the cosmos. The universe does not always reveal its most powerful objects through light. Sometimes the most important thing in the image is the thing that is missing. A galaxy can look dead. A black hole can give off nothing. And yet, the stars around it still carry the truth in their orbits, written in velocities and dispersions and the quiet mathematics of gravity. Something with the mass of 6 billion suns is hiding in the dark. Webb photographed the galaxy that contains it, but the black hole itself remains unseen, a presence known only by its influence, an engine known only by the silence it left behind. And somewhere out there in the deep field, images already sitting in the archive, in the faint red smears and stretched arcs that no one has examined closely yet. There may be dozens more, hundreds more. A hidden population of the most massive objects in the cosmos, scattered across the early universe, invisible and patient, waiting for gravity to give them away. The silence of the cosmos is not empty. It is full of things we have not yet learned to see. And now, for the first time, we have a way to listen, not for light, but for the motion of stars caught in the grip of something enormous and unseen. The search is just beginning. The first whisper has been heard. And what the universe is telling us, through the orbits of ancient stars around an invisible center, is that the quiet places are not empty. They are where the real power hides,